Okay, so now we are streaming live on YouTube. Hi, welcome everyone. Good morning. And
Time we were
so, as usual, if you have any questions or doubts regarding any of the material in between of the talk, you can unmute yourself and ask the speaker. And the slides have already been put up in the chat box just in case you want to go back and forth while the speaker is talking. So you can refer there. Other details are also there on the web page. You can check out. And today we have Amit Roy from IISER Mohali, and he'll be speaking on standard monomials of one skeleton ideals of graphs. Amit, please take over.
Thank you. So, good morning, everyone, and welcome to my talk. So, first, I would like to thank the organizers and Professor Priyobrat Deshpande for inviting me and for giving me an opportunity to talk here. So, the title of my talk is Standard Monomials of One Skeleton Ideals of Graphs. So, this is based on a joint work with Professor Chanchal Kumar and Ms. Gargi Lather. So, first, I will give an outline of the talk. So we'll define a notion called parking functions, which is related to the parking of n number of cars in a linearly ordered parking space. Then we'll consider a generalization of this notion parking function. This is called the G parking functions. These are defined for a graph G, and we'll see that how the number of G parking functions are related to the spanning trees of the graph. After that, we will define what is called the G parking function ideal. This is an algebraic analog of the G parking functions. And we will also consider the Laplace matrix of a graph and see how these two things are related. Then we will consider the one skeleton ideals. So these one skeleton ideals, these are defined by Dr. Mann, and he defined these ideals and proved some algebraic and combinatorial properties for these ideals. So we'll see how the one skeleton ideals are related to the signless Laplace matrix and the spanning tree subgraphs of the graph G. So first, let us see the definition of parking function. So a parking function is related to the notion of parking of n number of cars in a linearly ordered parking space. So suppose there are n cars C1, C2 up to Cn, and each car Ci has parking preference Pi. So here Pi is a number in between 0 to n minus 1. The rule is that the car Ci will go to its preferred space Pi, and if it is unoccupied, then it will park there. Otherwise, it should go forward. So the rule is it cannot go backward. Now, in this rule, we say that the parking preferences P1, P2 up to Pn, these are parking function if all the cars can park. So this is the definition of parking function. So more mathematically, a parking function of length n, this is a sequence of non-negative integers p1, p2 up to pn, such that its non-decreasing rearrangement pi1 less equals to pi2 up to pin satisfies this condition pij less than j for j in between 1 to n. Equivalently, the number of I such that pi less than r should be greater equals to r for each r from 1, 2, 3 up to n. So from the definition, note that if P1, P2 up to Pn, this is a parking function, then one of the Pi should be equals to 0. This is because in this condition, Pij less than j, if we put j equal to 1, then we have that Pi1 less than 1. Since we are considering Pi's to be the non-negative integers, so we will have that Pi1 should be equal to 0. So one of the Pi should be 0 if it is a parking function. Moreover, if P1, P2 up to Pn, this is a parking function, then a rearrangement of Pi or a permutation of Pi, this is also a parking function. So for example, the sequences 0, 0, 0, 1 and 1, 0, these are the examples of all parking functions of length 2. Also, the sequences 2, 1, 0, 1, 0, 1, these are examples of parking functions of length 3. For example, if you take 2, 1, 0, then this is a parking function because it has a non-decreasing rearrangement 0 less than 1 less than 2. where pi1 is equals to 0, pi2 is 1 and pi3 is 2, such that this condition pij less than j for j in between 1 to 3, this condition is satisfied. So therefore this is a parking function. However, 1 1 1, this is not a parking function, because as we noted earlier, in order to in order to it become a parking function, we must have one of the pi should be equal to 0. However, this is not the case here. So 1 1 1 is not a parking function. So one can check that there are 16 parking functions of length 3. So in general, Onheim and West, they defined this notion of parking function, and they proved that the number of parking functions of length n is n plus 1 whole power n minus 1. So next we will see some, one generalization of the parking function. This is called the G parking function. So this is defined for a graph G. So let G be a graph on the vertex set 0, 1, 2 up to n. So we will always consider undirected multigraphs without loops. And the vertex 0, this is a special vertex of G. This is called the root of G. For I and j in between 0 to n, suppose aij or aji, it denotes the number of edges between I and j. And aii is equals to 0. This is because we have always considered G to be loopless. Also, for every non-empty subset A of the set 1 to up to n, we consider the integer d of I, which is by definition sum of aij, where j does not belongs to A, and we are considering I belongs to A. So d of I is basically the number of edges incident to the vertex I whose other endpoints are not in A. For example, if we take A to be the singleton I set, then d of I is actually di, where di is the degree of the vertex I in G. So with these notations, we now define what is called the G parking function. So let G be a graph on the vertex set 0, 1, 2 up to n. A sequence p1, p2 up to pn of non-negative integers is called a G parking function if for any non-empty subset A inside 1, 2 up to n, there exists some I belongs to A such that pi is less than dA of I, where dA of I is the number of edges incident to the vertex I whose other endpoints are not in A. So we will see that these G parking functions are actually a generalization of the classical parking functions that we have introduced first. So for this, we recall some definitions of well-known families of graphs. So fix two non-negative integers a and b, and let G equal to kn plus 1 a comma b. This is the complete multigraph on the vertex set 0, 1, 2 up to n with edges 0i of multiplicity a and the edges I comma j of multiplicity b. So the edges 0 comma I, these are called the rooted edges, and the edges I comma j, these are called the non-rooted edges. So the complete multigraph kn plus 1 a comma b, this is a multigraph on the vertex set 0, 1, 2 up to n such that the rooted edges has multiplicity a and the non-rooted edges has multiplicity b. If we take in particular a equal to b equal to 1, then the graph kn plus 1 1 comma 1, this is called the complete simple graph, and this is also denoted by kn plus 1. Any subgraph of the complete simple graph, we will call this graph as a simple graph only. So we will see that the kn plus 1 parking functions are actually the ordinary parking function or the classical parking functions. So therefore, by the theorem of Onheim and West, we can show that the number of kn plus 1 parking functions is n plus 1 power n minus 1. More generally, one can show that the number of kn plus 1 a comma b parking functions is a times a plus bn whole power n minus 1. So these are some examples of number of parking functions. So now we want to prove that these kn plus 1 parking functions are actually the ordinary parking functions. So the statement of the proposition is that if g equal to kn plus 1, then the g parking functions are the ordinary parking functions of length n. So we will now prove this. Suppose that there are non-negative integers p1, p2 up to pn, which are kn plus 1 parking functions. Now recall the definition of G parking function, which says that for each non-empty subset A of the set 1, 2 up to n, there exists some IA belongs to A such that PIA should be less than D of I. where d of I is the number of edges incident to I whose other endpoints are not in A. So this condition is satisfied for this sequence of integers p1, p2 up to pn. So in particular, we can take the set A1 to be the set 1, 2 up to n. This is the whole set. Except 0 is not. So we are not considering 0 in this set, 1, 2 up to n. So we have, by the definition, there exists some I1 belongs to A1 such that Pi1 should be less than dA1 of I. Now I is connected to the root vertex 0 only outside the set A1. Therefore, dA1 of I is equal to 1 here. So we have Pi1 is less than 1. Now if we take A2 to be the set A1 minus I1, then there exists some I2 belongs to A2 such that Pi2 should be less than dA2 of I. Again, here in this case, I is connected to the vertex 0 and I1 outside the set A2. Therefore, dA2 of I, it should be equal to 2. So we have Pi2 is less than 2. We can continue this way, and at the t stage we have that at to be equal to at minus 1 minus it minus 1, and there exists some it belongs to at such that pit should be less than dat of I, which we can calculate to be equal to t. So we have found a rearrangement of p1, p2 up to pn such that pij is less than j for each j in between 1 to n. Therefore, we can see that p1, p2, pn, this is actually ordinary parking function. So by the theorem of Konheim and OS, we have that the number of kn plus 1 parking functions is actually n plus 1 power n minus 1. So next, we will associate some matrices with the graphs. So let G be a graph, multi-graph on the vertexes 0, 1, 2 up to n. At the adjacency matrix A of G, this is a square matrix of order n plus 1 whose ijth entry is aij. So here the rows and columns of A of G, these are indexed by the vertices. And since we are always considering undirected graph, so the adjacency matrix will be a symmetry matrix. Moreover, since our graphs are loopless, we will have that the diagonal entry of AG is equal to 0. Each diagonal entry is 0. Now we consider the degree matrix. So the degree matrix, this is a diagonal matrix of order n plus 1 whose ith entry is di, where di is the degree of the vertex I. Using these two matrices, we can define a matrix called the Laplace matrix. So the Laplace matrix is denoted by Lg, and this is the difference d of g minus a of g. Similarly, we can define signless Laplace matrix, which is denoted by Qg, and this is the sum d of g plus a of g. Now, since we have defined Lg and Qg, from that we can define what is called the truncated Laplace matrix and truncated signless Laplace matrix. So the truncated Laplace matrix Lg tilde, this is obtained from Lg by deleting the first row and first column. That is the row and column corresponding to the root vertex 0. Similarly, the truncated signless Laplace matrix is obtained from the signless Laplace matrix Qg by deleting the first row and first column. So the truncated or reduced, we also call this matrix reduced Laplace matrix or reduced signless Laplace matrix. These are Lg tilde and Qg tilde. So for example, we look at this graph. So this is the graph obtained from the complete simple graph K4 by removing the edge 0, 2. So for this graph, we have the adjacency matrix AG. This is a square matrix of order 4, and its ijth entry is aij, where aij is the number of edges between I and j. So from the definition, so the diagonal entries are 0, and the for example the 0, 2 entry is 0 because there is no edge between 0 and 2. We have the diagonal matrix D of G. This is diagonal 2, 3, 2, 3. This is because the vertex 0 has degree 2, 1 has degree 3, 2 has degree 2, and 3 has degree 3. And then we have the Laplace matrix Lg. This is d of g minus a of g. So the diagonal entry of Lg is the diagonal entry of the diagonal matrix d of g, and the off diagonal entries are off diagonal entries of a of g with a negative sign. and we have the QG, this is AG plus DG. So we can see that the matrix QG, this is obtained from LG by removing all the negative signs. This is why the matrix QG is called signless Laplace matrix. So this is the Laplace matrix and this is the signless Laplace matrix for this graph G. Then if we delete the first row and first column, that is the row and column corresponding to the vertex 0, then we will get the truncated Laplace matrix. And similarly, deleting the first row and first column from QG, we will get the truncated signless Laplace matrix. This is QG tilde. So LG tilde and QG tilde for this graph, these are these two matrices. So after this example, so we define what is called a spanning tree. So a spanning tree of a graph G, this is a subgraph T of G such that the vertex set V of T is same as the vertex set of G and T does not contain any cycle. So in other words, a spanning tree is a spanning subgraph of G which is also a tree. For the graph in the above previous example, we can check that there are 8 spanning trees. So these are the 4 spanning trees and these are 4 more. So these are the 8 spanning trees for the graph G. And we can also check that the determinant of LG tilde is also 8. So for this graph, we have determinant of LG tilde is equal to the number of spanning trees of G. However, this is true in general. So which is called the matrix tree theorem. So the matrix tree theorem says that if Ng denotes the number of spanning trees of a graph G, then Ng is equal to determinant of Lg tilde. So we have that determinant of Lg tilde is also given by the number of spanning trees of G. In this context, we have this theorem by Gabrielov, which says that the number of G parking function of a graph is given by determinant of Lg tilde, which is again by the matrix tree theorem, the same as the number of spanning trees of G. So therefore, we have that the number of G parking functions and the number of spanning trees of a graph are same. So this is the Gabrielov's theorem. So we have defined G parking functions. Now we are going to see an algebraic analog of these G parking functions. So these are called the G parking function idea. Postonikov and Shapiro, they introduced the G parking functions in an algebraic context and they reproved above theorem, that is Gabrielov's theorem. So they defined a monomial ideal Mg corresponding to a given graph G, and this ideal is called the G parking function ideal. So to define this ideal, let K be a field and R be the polynomial ring in n variables x1, x2 up to n. Then if G is a graph on the vertex set 0, 1, 2 up to n, the G parking function ideal Mg is a monomial ideal generated by the monomials Ma, where A is any non-empty subset of the set 1, 2 up to n, and Ma is the monomial product of xi power di, where I belongs to A. So recall that d of I, this was the sum of Aij, where j does not belong to A. In other words, d of I was the number of edges incident to the vertex I whose other endpoints are not in A. So for example, if we take A to be the singleton set I, then d of I is di. Therefore, the monomials xi power di, these are in the generating set of Mg, where di is the degree of the vertex I and if we take A to be equal to I, j, then d of I, this is di minus aij. Number of A is to be equal to dj minus aij. So the monomials xi power di
Amit?
minus aij and xj power, yeah, dA of j is to define.
Hello.
Hello?
I think there is some disturbance in the voice. For a while, we couldn't hear anything, and then your voice is little breaking. Can you check your internet connectivity, please?
I am connected to LAN in the.
Just for a while, it had gone. Now it again seems fine. So if you could just repeat the same thing after what you said, what MA is.
Okay. So MA is this monomial. So can you hear me now?
Yes, yes.
Okay.
Thank you.
So MA is this monomial product of xi power d of I, where I is any non-empty subset of the set 1, 2 up to n. So here, for example, if we take d, so recall the definition of dA of I. So this is the number of edges incident to the vertex I whose other endpoints are not in A. So if we take, for example, A to be the singleton set I, then dA of I is di, where di is the degree of the vertex I. So therefore, xi power di, these monomials are in the generating set of Mg. Similarly, if we take A to be equals to I comma j, then dA of I is di minus aij, where aij is the number of edges in between I and j, and dA of j, this is dj minus aij. So the monomials xi power di minus aij times xj power dj minus aij, these are also in the generating set of Mg. So in this way, for a given graph, we can determine all the generators of Mg. So from the definition, note that Mg is an Artinian monomial ideal. So that R mod Mg is a finite dimensional vector space where K is a field over the field K. So if we are given some non-negative integers p1, p2 up to pn, then we can associate this sequence p1, p2 up to pn to a monomial, which we denote by x power p, which is by definition product of xi power pi. Now from the definition, we can deduce that the sequence p1, p2 up to pn, this is a g-parting function if and only product of xi power pi, this monomial does not belong to Mg. So all those monomials which does not belong to Mg, these are called the standard monomial of R mod Mg. So therefore, P1, P2 up to Pn, this sequence of non-negative integers, this is a g-parting function if and only product of xi power pi is a standard monomial of R mod Mg. So in this context, Postnikov and Shapiro, they reproved Gabriel's theorem. So they proved that for a graph G on the vertex set 0, 1, 2 up to n, so the dimension of R mod Mg, that is the number of standard monomials of the g-parting function ideal Mg, is same as determinant of the truncated Laplace matrix Lg tilde, which is again by the matrix tree theorem is same as the number of spanning trees of G, which we denote by Ng. So the number of standard monomials of Mg, R mod Mg, is same as the number of spanning trees of G. So this is Postnikov and Shapiro's theorem. Now, Dr. Men, so before going to the another generalization of Mg, we look at this example. So this is the graph G as before. So this is obtained from K4 by removing the edge 0, 2. So for this graph, we can check that the g-parting function ideal is generated by these monomials. So for example, we have this monomial x1 cube because the vertex 1 has degree 3. Similarly, we have x2 square and x3 cube because the vertex 2 has degree 2 and 3 has degree 3. And we have the monomial x1 square, x3 square because we can write it as x1 power 3 minus 1 times x3 power 3 minus 1, where both the vertex 1 and 3 has degree 3 and there is an edge in between 1 and 3. So this way, this monomial x1 square, x3 square will come. So in similar way, we can define all the generating set for this ideal. And one can check that the standard monomials of R mod Mg are these. So there are 8 monomials which does not belongs to the ideal Mg. And if we take the exponents of these monomials, then these are the g-parting functions. So for example, 1, 0, 0, this is the exponent of x1, and 0, 1, 1, this is exponent of the monomial x2 times x3. So
Just to interrupt, in the last element in Mg, which you write as x1, x2 power 0, x3, is that a typo?
No. That means x1 power 1. I mean x2 is omitted. I mean, so x2 power 0, this would be equals to 2 minus 2. We can write here 2 minus 2.
Okay. So maybe
Because,
I missed some previous part, but do we take these elements here only when all of them are adjacent to each other, or?
No, you can take, so in the definition, so here A is any non-empty subset, right? A can be any non-empty subset of 1 to up to n.
Yeah.
Then we can define this monomial xi power d of I. So for this case, x1, x2 power 0, x3, here A is the set 1, 2, 3.
Mm-hmm.
So this is the monomial corresponding to the set 1, 2, 3. So then x1 power, so what will be x1 power here? So x1 power will be the degree minus the total number of edges, I mean, which are in between 1, 2 and 3, right? So except 1, 2 and 3, 1 is connected to only 0. So there is only one edge connected to 1, which is outside the set 1, 2, 3. Therefore, we have x1 power 1. However, for the
Okay,
vertex
okay,
2,
okay. Yeah,
so
since it is not connected to 0, its power is 0.
0, yes.
Okay, okay. Thanks.
So okay, so the exponent, these will be the z parking functions for this idea. So Dr. Mann generalized this notion of g parking function ideal, and he introduced what is called the k skeleton ideals. So here k is an integer in between 0 to n minus 1. So these ideals are by definition sub-ideals of mg. So this is the definition of k skeleton ideal. Let G be a graph on the vertex set V of G to be equal to 0, 1 to up to n, and k is an integer in between 0 to n minus 1. Then the k skeleton ideals mgk, this is generated by the monomials ma, where a is again a non-empty subset of 1 to up to n, and ma is the monomial product of xi power d of I belongs to a, with extra condition that the cardinality of a is at most k plus 1. So this is the extra condition than the g parking function ideal. So because of this condition, this is called the k skeleton ideal. For example, if you take k equal to n minus 1, then we are saying that the cardinality of a should be less equals to n. But a is a subset of 1 to up to n. So if we take k equal to n minus 1, then ma is a monomial corresponding to all the non-empty subset of 1 to up to n. So the k skeleton ideal mgk for k equal to 1, k equal to n minus 1, this is nothing but the g parking function ideal mg. So this is the definition of k skeleton ideal. So we look at one example. Suppose C5, this is the cycle graph on the vertex set 0, 1, 2, 3, 4. And we consider the case k equal to 1. So in this case, we have MC51. This is generated by these monomials, where each of the xi has degree 2. I mean, each of the xi has exponent 2 because each of the vertex has degree 2. And we have x2 times x3 because this can be written as x2 power 2 minus 1 and x3 power 2 minus 1, where both the vertex 2 and 3 has degree 2, and there is an edge in between 2 to 3. So this way we get this monomial x2 times x3. And similarly, we can get other monomials also. So our focus is only on the k equal to 1 case. So we will only consider the one skeleton ideal case. Now recall that for g parking function ideal mg, we have that the number of standard monomials is given by the determinant of the truncated Laplace matrix Lg tilde. However, for this one skeleton ideal case, we will have some interpretation in terms of the truncated signless Laplace matrix Qg tilde. So Dr. Mann proved that for the complete simple graph kn plus 1 on the vertex set 0, 1 to up to n, the number of standard monomials of the one skeleton ideal kn plus 1, this is given by the determinant of the truncated signless Laplace matrix of kn plus 1. So this is proved by Dr. Mann. So then we consider this. We have proved this theorem. So let R be an integer in between 0 to n, and G and R be the graph obtained from kn plus 1 by deleting exactly R number of edges which are connected to the root 0. So we are only deleting the rooted edges. R number of rooted edges we have deleted. So in this case, in this graph, for this graph G and R also, we proved that the number of standard monomials of one skeleton ideal is same as the determinant of the truncated signless Laplace matrix of G and R. And we have explicitly calculated what is this number. So this number is n minus 1 power n minus r minus 1 times n minus 2 power r minus 1 times 2n minus 1 into n minus 2 plus r. So in this theorem, if you put r equal to 0, then gn 0 is basically kn plus 1. So we can get that Dr. Mann's theorem from here. So I should remark that one can also prove that if we take g to be the complete multigraph kn plus 1 a comma b, then one can also prove directly that the standard monomials, number of standard monomials of the one skeleton ideal for the graph kn plus 1 ab, this is same as determinant of its truncated signless Laplace matrix. So for the multigraph case, we can prove a generalization of this theorem. So this is the theorem. So let G be a multigraph on the vertexes 0, 1, 2 up to n. This is obtained from the complete multigraph kn plus 1 a comma b by deleting some edges through the root 0. So in this case also, the dimension of the Artinian monomial, the quotient of the Artinian monomial ideal, this is same as the determinant of QZ tilde. So here we are writing Rn instead of R to indicate that R has n number of variables x1, x2, xn, or alternatively the graph G has n number of vertices, I mean n number of non-rooted vertices, 1, 2 up to n. So this is why we are writing Rn. So I will give a brief sketch of the proof of this theorem. So we will prove this by induction on n, that is on the number of non-rooted vertices. Here it should be non-rooted vertices. So we are considering the suppose G is this graph, G is obtained, I mean G is of this form, that is G is obtained from kn plus 1 a comma b by deleting some edges through the root 0. So the adjacency matrix AG, this is Aij, where A0i is Ai. So here Ai is less equals to A, and Aij is B because we are not deleting any non-rooted edges. Now suppose E0 be a fixed edge from 0 to J in G, and we consider the graph G prime. This is obtained from G by removing the edge E0. And suppose G double dash, this is the graph on the vertex set V of G minus J. So the cardinality of the vertex set is cardinality of Vg minus 1. And it has rooted edges A0i tilde, this is Ai plus B, where Ai is as in the graph G, and Aig tilde, where these are the non-rooted edges, this is B. So for example, suppose G is this graph, I mean this is as before obtained from K4 by removing this rooted edge 02. Then we are taking the edge, the fixed edge E0 to be this 03. So G prime is obtained from G by removing this edge 03. So in this case, I mean in this example, we have J equal to 3. Therefore G double prime, this will be a graph on the vertex set 0, 1 and 2 only. And we will have one more edges attached for 0, 1 and 02. So 01 has the edge 01 has multiplicity 2 and the edge 02 has multiplicity 1. And the non-rooted edges, these are multiplicity as before, this 1. So in the graph G we have 1, 2 has multiplicity 1, and in G double prime also we have multiplicity 1 in between 1 and 2. So this is one example of how we are considering G prime as G double prime. So for these graphs, we can prove that the number of standard monomials of the one skeleton ideal of Mg, this is sum of the number of standard monomials of one skeleton ideal of G prime and G double prime. And we can also prove that the determinant of QG tilde, this is sum of the determinant of the truncated signless Laplace matrix of G prime and G double prime. So here we are writing Rn minus 1 in this second case because the G double prime, this has one less vertex than G. And since G double prime has one less vertex, by the induction hypothesis, we can write the dimension of Rn minus 1 by Mg double prime 1. This is equal to determinant of Qz double prime tilde. So from these two equations, then we can write that dimension of Rn mod Mg1 equals to determinant of Qz tilde if and only if the number of standard monomials of the one skeleton ideal of G prime is same as determinant of the Qz prime tilde. Now we have remarked earlier that one can prove this theorem for the complete multigraph Kn plus 1 a comma b. Thus we can prove the theorem for this graph G by considering the complete multigraph Kn plus 1 a comma b and then deleting the rooted edges one by one. So this is how we can prove this theorem. So far we have seen examples of graph for which the standard monomials of one skeleton ideal, this number is same as determinant of qg tilde. However, unlike the case for the g parking function ideal, this is not always true. I mean, there are examples of graph where this equality does not hold. For example, if we consider graph G to be this graph, this is obtained from K4 by removing the non-rooted edges 2, 3. Then for this graph, one can calculate the one skeleton ideal is generated by these monomials, and the truncated Laplace matrix is this matrix. So one can check that the number of standard monomials for the one skeleton ideal is 13 and the determinant of qg tilde is 8. So here we have that dimension is strictly bigger than determinant. So after a number of calculations, Dr. Mann posed this question. So he asked that for any graph G, is it true that the number of standard monomials of one skeleton ideal is bounded below by the determinant of qg tilde? So we have answered the above question in the affirmative for multigraphs. So we have proved that if G is a multigraph on the vertexes 0, 1, 2 up to n, then the number of standard monomials of the one skeleton ideal is always bounded below by determinant of the truncated signless Laplace matrix of the graph G. So we have proved this theorem using some results from linear algebra. However, Dr. Mann also proposed one way to prove this. So he proposed one combinatorial way to prove this inequality. So I will explain now what is this way. So we recall that the determinant of the truncated Laplace matrix LG tilde, this counts the number of spanning trees of G. So where a spanning tree T of G, this is a connected spanning subgraph of G which is acyclic. That is, T is a tree with the vertex set same as the vertex set of G. Now for the matrix QG tilde, the determinant of QG tilde can be expressed in terms of certain Q subgraphs of G. So I will define what are these Q subgraphs. So a Q subgraph is a subgraph of G whose connected components are either trees or unicyclic graph with odd cycles. For example, the trees are always Q subgraph. However, these are two examples of Q subgraph which are not tree. So these are two examples of Q subgraph of the simple graph K5. And in each of these examples, we have two components, and one of the component is unicyclic with a cycle of length 3. So these are the Q subgraphs of K5, and we can express the determinant of QG tilde in terms of these Q subgraphs. So this is the proposition by Dr. Mann. So he showed that for any graph G, the determinant of QG tilde, this can be expressed as sum of 4 power CH, where H is a spanning Q subgraph of G with C of H number of unicyclic components and one tree component which contains the vertex 0. So this is the expression of determinant of QG tilde in terms of these Q subgraphs. Now, so Dr. Mann proposed how we can prove this. So suppose we want to prove this inequality, so that number of standard monomials of one skeleton ideal is bigger or equal to determinant of QG tilde. And we have this interpretation of determinant of QG tilde in terms of this Q subgraph. So one way to prove is that we can assign each Q subgraph H of G of this form. That is, the Q subgraph has CH unicyclic component and one tree component which contains this vertex 0. So we can assign this Q subgraph to a collection of 4 power CH standard monomials of R mod MG1. So this will be an injective map. Actually, this will be a weighted injective map from the collection of spanning Q subgraphs and to the collection of the standard monomials. So each Q subgraph will be mapped to 4 power CH number of standard monomials. For example, we know that a tree is a Q subgraph, and if we take H to be a spanning tree of G, then we have the CH to be equal to 0. Thus, a spanning tree will be associated to 4 power G, that is 1 standard monomials of R mod MG1. Now, recall from the definition of MG1, we know that the mg1 is a sub-ideal of the g parking function ideal mg. So therefore, the standard monomials of mg are among the standard monomials of mg1. And we know that the exponent of the standard monomials, these are given by g parking functions. So there are some bijections in between the g parking functions, that is the standard monomials of mg, and the spanning trees of g. So if we can manage to give such a this injective map from the spanning Q subgraph to standard monomials of mg1, this could extend one of those bijection in between spanning trees and the standard monomials of mg. So this is one combinatorial way to prove this inequality. But we have proved this inequality using some algebraic manipulation and some results from linear algebra. So I will. So we'll see this proof shortly. So we want to prove this inequality, that dimension of R mod mg1 is greater or equals to determinant of qz tilde. So for this, we introduce some notations. So suppose M and N is the square symmetric matrices over non-negative integers, and Gn is the collection of this matrix H, where H is equal to Bij, and the diagonal entries Bii, this should be greater or equals to maximum of Bij, where J is not equals to 1. So what we mean is that H is a symmetric square symmetric matrix whose each diagonal entry is bigger or equal to all the entries of the diagonal, all the entries of the row or column in which it belongs. So this is the definition of H. So for this H, if we denote alpha I to be the diagonal element Bii, then we can associate a monomial ideal JH, which is generated by the monomials xl power alpha L, where L is in between 1 to n, and xi power alpha I minus Bij times xj power alpha j minus Bij, where I and j are non-zero and they are in between 1 to n. So this is the this way we can associate a monomial ideal with respect to H. For example, suppose we have this matrix H. So here the matrix is 3 1 2 1 3 1 2 1 4, and the each diagonal entry is bigger or equal to all the entries of the row or column in which it belongs. For example, 4 is bigger than 2 and 1. So 4 belongs to the third row and third column. So, and we see that 4 is bigger than 1 and 2. So for this H, we can define this monomial. So here x1, we have x1 cube because the 1 1 entry is 3. And similarly, we have x2 cube and x3 power 4 because the 2 2 entry is 3 and 3 3 entry is 4. And we have x1 square, x2 square, because we can write x1 square, x2 square as x1 power 3 minus 1 and x2 power 3 minus 1, where 3 is both the first diagonal entry and second diagonal entry, and 1 is the crossing point in between these two entries. So that is why we have x1 square and x2 square. Similarly, we can write all these monomials. So if we take H to be equal to QZ tilde in particular, where QZ tilde is a truncated Laplace matrix of the graph G, sorry, truncated signless Laplace matrix of the multigraph G, then we can check that JH, the ideal JH, will be equal to MG1, where MG1 is the one skeleton ideal of the graph. In this context, we have proved that if H belongs to Gn is a positive semi-definite matrix, then the number of standard monomials of the ideal JH is always bounded below by determinant of H. So since QG tilde, this is always a positive semi-definite matrix, since QG tilde is always a positive semi-definite matrix, we will have that dimension of Rn mod mg1, this is greater or equals to determinant of QG tilde. So in order to prove this theorem, we have used two theorems. One of them is Fisher's inequality. So it says that if M is a block matrix A, B, B star C with square matrices A and C, then determinant of M, this should be less equals to determinant of A times determinant of C. So this is one theorem we have used, and we have also used current while inequalities. So it says that if M is a Hermitian matrix and its real eigenvalues are arranged in a non-decreasing order, lambda 1 of M less equals to lambda 2 of M and so on. Then for any two Hermitian matrices M1 and M2, we have lambda I of M1 plus M2. This is less equals to lambda I plus j of M1 plus lambda n minus j of M2.
Amit,
So using
how much is left?
I will give this proof. I mean, so is it okay? I can stop here.
No, I mean, if you can just quickly go through it, it's fine. You can take 5 more minutes.
Okay.
Is that okay?
Yes, yes.
Okay.
So using this two theorem, we can prove the theorem that the number of standard monomials of JH is bigger or equal to determinant of H. So we will prove this by induction on n, where n is the order of H. So suppose for n equal to 1 and 2 case, this inequality we can check directly. Actually, this inequality will be an equality. And for bigger n, so suppose H is the matrix Aij n by n and alpha I to be the diagonal entry Aii, and if B is the maximum of Aij, then we can after a permutation of row and column, we can write H in this form. So where the entries A r plus 1 comma j, these are all B, and entries A I comma r plus 1, these are all less than B. So for this H, we can write all the monomials in this way, and we want to take colon of JH with respect to the monomial xr plus 1 power alpha r plus 1 minus B. Then the colon ideal and the ideal generated by JH comma this ideal, this we can associate to other two matrices. So these two matrices are H1 and H2. So H1 is the principal r plus 1 cross alpha r plus 1 matrix whose r plus 1th entry is replaced by B, and H2 is the matrix obtained from H by removing the r plus 1th row and r plus 1th column. And we can show that JH colon this monomial xr plus 1 power alpha r plus 1 minus B, this we can write in terms of JH1, and JH comma this ideal, this we can write in terms of JH2. Then using the short exact sequence, so here mu is the multiplication by xr plus 1 power alpha r plus 1 minus B, and mu is the quotient map. So using this short exact sequence, we'll get one formula of Rn mod JH in terms of the dimension of Rr plus 1 by JH1 and dimension of Rn minus 1 by JH2. And by induction, since H2 has order n minus 1, we will have dimension of Rn minus 1 by JH2 will be greater equals to determinant of H2. So, and also we have by linearity of determinant of H is alpha plus 1 minus B times determinant of H plus determinant of T, where T is this matrix. So this is obtained from H by replacing only the R plus 1 at diagonal entry by B. And then using current-while inequalities and Fisher's inequality, we can prove that determinant of T is less equals to this quantity. And this will give that determinant of H is less equals to dimension of Rn mod GH. And as a corollary, since the truncated signless Laplace matrix QG tilde is a positive semi-infinite matrix, we can answer Dr. Mann questions. This is the main corollary, and these are the references. Thank you.
Anyone has any questions? Okay, maybe there are no questions. Let's all unmute ourselves and thank the speaker.
Thank you.
Thank you.
Thank you, Amit.
Thank you.
So next week we'll meet again, and next week actually we are meeting on 2 days, Wednesday and Thursday, because the talk on Thursday is going to be a continuation of the talk which will happen on Wednesday. We'll send out 2 separate emails for the talks, or within the same email we'll give the information about both the talks. So next week we are meeting twice, Wednesday and Thursday. Details are already uploaded on our webpage. You can go through the details, and the